Hey guys, welcome back. Today we're going to talk about section 8.2, area of a surface of revolution. But first, just a friendly reminder what we talked about last time. We talked about the arc length of a curve. So if we have a curve defined as y as a function of x, and we're looking at the length of, let's do this color, right here, we're looking at the length of a curve between the endpoints of the interval. So if I was to actually pick up that little piece and stretch it out, how long would that be? Well, the arc length we found last time without much explanation, but if you want to go over the derivation, be happy to set up a time to do that with you. We're going to integrate this function over the interval a, b. It's going to be 1 plus the derivative squared all under the radical, and we're going to integrate with respect to x. If we had it defined as a function of y instead, it doesn't change much. Suppose we have this. This was h of y. And we wanted to know the length of the line from here to here between endpoints. It doesn't have to stop necessarily, but we're only concerned about what happens between and here, and we were to pick this up. The length of this function can be expressed the same way. We would just solve the function for, get x as a function of y, and would integrate from c to d, our integration limits on the y-axis. And this time it would just be h prime of y squared dy. Right, and that's what we talked about last time. So hopefully you're working on those problems and making some progress. Today we're going to talk about the area of a surface of revolution. So let's suppose we think back to our the stuff we talked about in chapter 6. We have a function defined on a closed interval a, b. We're going to rotate it. And for the sake of this section, we either stick around the x-axis or we stick around the y-axis, so we're not doing anything too funky. We're going to rotate it about the axis, and we're going to see how the surface area behaves as opposed to the volume. Last time we talked about the volume, so if we rotate this about this axis, it would kind of give us this sort of shape. I'm going to do it with, let's do this color instead. Right? It's going to give us, this particular function would give us a bowl shape. But instead of calculating the volume of the bowl, we're just going to look at the surface area and how much material would we need to cover the surface of this shape obtained by rotating the function f of x about the x-axis. The answer to that would integrate from a to b. The function is defined from a to b on the x-axis. 2 pi f of x 1 plus the derivative of f of x squared dx. So we're pretty much taking the length of this line. So what we're doing is we're breaking it down into little pieces. And we're looking at the surface area of one of the disks. And the height of the surface area is defined by the function itself. We saw that the length of that line, or the height of one of these disks, was found by integrating this. And then 2 pi r would be the area of one of the surfaces. So that would be the area of the surface of revolution when the function f of x is rotated about the x-axis. Now, if we decided instead to rotate something about the y-axis, so let's take this shape, and x is expressed as a function of y, and we rotated it about the y-axis. So make sure you read the question carefully. Are we rotating about the x-axis or the y-axis? We're going to get this shape, and the integral is going to get set up similarly. Just be integrating from c to d, 2 pi h of y, the square root of 1 plus h prime of y squared dy. So that would be the area of a surface of a solid of revolution obtained by rotating the function f of y about the y-axis. So let's look at a couple of examples. Let's determine the surface area of the solid obtained by, nope, I'm going to do that one second. Let's do this one first, the x one. Determine the surface area of the solid by rotating y equals the square root of 9 minus x squared about the x-axis. So we're going to, let's see, we could draw this maybe. I'm not quite sure. Let's take a look at what this looks like. Y equals, I'm just curious, square root of 9 minus x squared. I'm not sure if I'm opening a can of worms here, but let's take a look. Ooh, I don't see very much. Zoom 6. There we go. All right, so looks like we have this a semicircle of radius 3, right? And we're going to rotate this about the x-axis. We're actually just looking at the area of a sphere. So using geometry, we could calculate this, but we're going to do it using calculus. So what we have here is, my function f of x, or y, f of x, is equal to the square root of 9 minus x squared. We take the derivative, 1/2. Remember, this is just 9 minus x squared to the 1/2 power. Bring the 1/2 out front, leave what's inside alone, drop the power by 1, times the derivative of what's inside. So clean that up a little bit. Those 2's cancel out. I'm going to get negative x all over the square root of 9 minus x squared. So therefore, the surface area can be found integrating from -2 to 2. Actually, it's not the entire sphere. I take that back because the entire sphere would go from here to here. So we're only doing part of it. So it's like a sphere with the ends cut off. Sort of like an ottoman. That's the shape that comes to mind for me. So it's going to be 2 pi f of x square root of 9 minus x squared times the square root of 1 plus negative x over the square root of 9 minus x squared dx. Ooh, that's looking a little scary. All right, so we got to clean this up. My guess is this is going to come out nicer than we expect. They typically do, although it might take some tricky algebra. So I'm going to integrate this from -2 to 2 pi square root of 9 minus x squared. Let's see, that's going to become, I'm going to do 1 plus negative x squared is x squared, because negative x times negative x would be positive x squared. And then 2, we square the 9 minus x squared, right? Then we find a common denominator so we can add the fraction under the radical. So this is great practice with for our integration skills. So we're going to find the common denominator would be 9 minus x squared. So we're going to integrate from -2 to 2 pi square root of 9 minus x squared. This is going to become 9 minus x squared plus x squared all over 9 minus x squared. Use a common denominator, 9 minus x squared over 9 minus x squared. Oh, look how beautiful this is cleaning up. -2 to 2 pi 9 minus x squared. This is just going to become 9 on top over 9 minus x squared. Distribute the radical to the numerator and the denominator. This is going to be 3 over the square root of 9 minus x squared. Those cancel. We're actually just integrating the constant 6 pi. And when we integrate the constant 6 pi with respect to x, we get 6 pi x from -2 to 2. Plug in the upper and lower limits, we'll get 24 pi. So therefore, that's my final answer. The area of the surface of revolution obtained by revolving this semicircle right here. So if we revolved this, it would come down like this. It would sort of be, like I said, it's like an ottoman to me. right? And how much fabric would we need to cover that ottoman? There we go. It would be 24 pi units squared, because area is units squared. Okay, not too terrible. All right, let's try one in spinning it about the y-axis. The process is the same. We just have to remember we have y equals the cube root of x. So in that case, x is equal to y cubed, because we're spinning it about the y-axis between 1 and 2. So the surface area can be found by integrating from 1 to 2 pi, and h of y, the function h of y would be y cubed, square root of 1 plus y cubed squared. Nope, don't do that. Oh, I messed it up. Did you see what I forgot to do? H of y is y cubed, so therefore the derivative is 3y squared, and that's what needs to go there. Don't make that mistake. So let's rewrite this. The surface area is going to be 1 to 2 pi y cubed. Don't forget to take the derivative. I did that in a couple of the problems with the arc length too. 3y squared, much better. And then this actually becomes much easier to integrate if you do the work properly. So really what I'm integrating is 2 pi y cubed, the square root of 1 plus 9y to the 4th dy. And let's take a minute. What are we going to use to integrate y cubed times 1 plus 9y to the 4th? Well, if you notice, we have y to the 4th inside the radical and we have y cubed on the outside. So this lends itself very nicely to substitution. So I'm going to let u equal what's under the radical. Then du would be 36 y cubed dy. And I'll proceed with the integration. So we're going to really integrate. I'll leave the 2 pi, pull the 2 pi out front. Y cubed is going to get replaced with 1/36 du. Right, because I bring that 36 over to the other side, I'm going to replace y cubed with 1/36 du. And I'm just taking the square root of u. Whoops, I made that really kind of far apart. So I'm really just integrating pi over 18, square root of u du, which is 2 u to the 1/2. We're going to add 1 to the power. Right. That's going to be pi over 27 u to the 3/2. So now let's return back to our original units. And I'm going to get, we're going to integrate. It's going to be pi over 27, 1 plus 9y to the 4th, all to the 3/2. We're going to integrate that from 1 to 2. Not pretty, but doable. So 1 plus 9 times 2 to the 4th. It's 145 to the 3/2 minus 10 to the 3/2. All right, so let's see. I guess we're just going to have to approximate this. So 145 to the 3/2 minus 10 to the 3/2. We're going to do times pi and divide that by 27. And it's about equal to 199.48 if we round to 2 places after the decimal. So these aren't nice numbers. There's no really nice way to simplify that, but the purpose is to get the process here and practice your integration. So that, guys, is 8.2. So you are going to read 8.2 in your textbook, text exercises. 1, 7 to 17 odd, finish 2.4 in XYZ. All right, next up is going to be chapter 11. Yeah, that's it for this. Talk to you guys soon.